are in lecture 14 of circuit switch networks. We will continue our discussion on synchronization. That is one topic which is probably still left for this particular discussion of switching in circuit switch network. So, we will quickly go to our this one, the one thing that we have started discussing. So, basically there are we have discussed already that there are two kinds of synchronization issue. One is for multiplexing and another one is for the switching. So, switching synchronization, a quick recapitulation, we have already discussed that switching the input or output are coming or going to multiple other geographical location. So, it is not necessarily that all those streams will be exactly clock synchronized or frame synchronized, they might not be. So, it is our job to actually make them synchronize. So, this is what we will have to do. So, at the input of switch, because it is getting heterogeneous input from different locations, different bit streams are coming. So, their data rate might not be exact or their clock rate might not be exactly matching, there must be slight desynchronization, it can always happen even if we try to synchronize it to the best of our ability, but there will be some desynchronization and that is something we have to take into account, because otherwise there will be huge problem. So, we have also discussed that there might be this desynchronization issue and we have to somehow at the input of the switch have to do something. So, that is where we started discussing about this elastic store. We have already discussed that, we have also given in the next slide probably we also have the discussion about its circuit. So, we will go into deep discussion of that. But before that, what is the other component that is used in circuit switch network, that is multiplexing. So, again in multiplexing what might happen, different streams are coming, they might also come from different location and again their bit rate might not match or their means exactly, of course, they will be almost similar, but there will be slight deviation in the clock frequency and their accordingly the associated rate. So, what do we do about this multiplexing also, because multiplexing takes exactly we talked about this bit interleaving or byte interleaving, they exactly takes from each stream within a particular 125 microsecond, they take equal amount of bits. But the problem is if they are desynchronized, then there might be or there is a possibility that if you count for a longer duration, the bits number of bits might not be equally counted for both the streams, because they have slight deviation in clock rate. So, that is another thing that we will have to account for. So, we have to give provision so that these things are properly accounted for. So, we will see how to do that. So, first let us talk about the one discussion that we have already done, that is the network synchronization. Okay. So, at the input of the switch, as we have shown in the previous slide. So, basically what you do, you have, so this is our switch, okay. So, this is the digital switch and we are probably getting output from here and input over here. Okay. So, what we are trying to do, every time whenever we are transmitting something, so that is the output that is going out. So, that should be switch output. So, therefore, it must have switch's own clock. So, we want to synchronize it with respect to the switch clock. So, any data that are coming, we cannot actually synchronize with each other, right, then it will be very difficult whom to synchronize with whom. So, therefore, we get the reference from switch, whatever clock it has, all others has to be somehow synchronized to that. So, we will see how to do that. So, basically from the switch transmitter we will take that actually clock and that particular clock, or from the switch we take the clock and that clock will fed to the elastic store. We have already demonstrated that. And also in the receiver part, whatever data is coming that might have a different clock. So, we recover that clock and actually that particular clock we fed to the elastic store. Now, elastic store will do something with these two reference clock and somehow make the data properly readable by the switch. Okay. So, this is something we have already started discussing about. Now, what we will try to do is, what is the problem? Probably last time we have discussed about this problem. So, briefly we will again discuss it for convenience. So, basically what happens, you have an input to the switch. Now, these datas are coming, let us say this is 125 microsecond frame. Okay. And let us say only 2 being multiplexed. Okay. So, they are coming one after another, okay, no problem with that. Okay. It just keeps on repeating. So, this is maybe data from 1, data from 2, data from 1, data from 2, they are keep on coming. Okay. In the other one, this is another port to the switch. So, this is also. Now, let us say I have slight desynchronization, okay, or slight higher this one. Okay. So, what will that mean? That probably the frame, because of the rates are slightly different, the frame might not contain. So, this if this is the frame, so there might be some slight desynchronization among the frames. Okay. So, they gets repeated similarly, and there might be some desynchronization, and because the rates are different. So, these how much they are misaligned, that also might keep on changing over time, because the rates are different. Okay. So, this is probably it is, if we take 8 bit, 16 bit is coming over here. So, that the other one might take little bit longer duration to transmit those 16 bits. So, it might happen that they are not completely aligned to each other. If this happens, but what we do, if we have a switch over here, suppose it has a space switch or it has a time switch, what it does for each one of them. So, within this there will be switching decision. So, clock means this has a clock, with that clock frequency it actually decides. So, this is the overall slot, and within this slot I have subdivided it into multiple small slot. So, 125 microsecond is subdivided, and over this slot I will apply some logic in the switch, maybe I will put them in bar stage. In the next one, we have already demonstrated that we will be probably putting another logic, maybe that time switch is in, sorry, this time it is in bar stage, earlier it was in cross stage. So, like this might happen. So, because of that, what will be happening? So, let us see target at the output what is going on. So, at the output what will be happening? So, let us say this is 3, this is 4, this is 3, this is 4. Now, because at the first this one, the switch is in cross state. So, therefore, one's data will come over here. Okay. So, the one's data will come over here. For the exact same duration, this data will actually get transferred over here, but the problem is because they are not synchronized. So, some partial data will be transferred, some partial portion of 3 and some portion of 4 will be transferred over here. This is a detrimental issue, because now the switching is not being done properly. So, this is what will be happening if we do not make the input synchronized at the byte level. If we can't do that, there will be problem. So, this is the problem we wish to solve through our elastic store. So, let us now try to see elastic store does. Okay. So, in the elastic store what happens? So, first we take the input signal, okay. We do the clock recovery, that is all fine. Then clock subdivided by 8, that means we are actually trying to identify the byte, exactly that 8 bit or byte boundary. Okay. So, if it is not byte interleaved, then it will be some other thing, of course. If it is 10 bit, then it should be 10 bit interval. So, it will be subdivided by 10, but right now we are assuming that it is all 8 bit. So, actually we do this byte interleaving, and that is why we are subdividing it by 8. That means, the byte boundary we are trying to find out. Okay. So, once we find out the byte boundary, what we do with that? We will see that later. So, first this data, it will be converted to serial to parallel. Okay. So, with this particular device, so let us say this one. Okay. So, it is first converted to serial to parallel, that means you keep a shift register, it will be keep on storing those data one by one, and then all 8 bits will be stored over here. So, bit number 1, 2, 3 like this, all 8 bits will be stored over here. Okay. Once they are stored, then this clock, if it is trailing edge or leading edge, with that clock actually whenever that divided by 8, that means byte boundary is identified. Once a byte boundary comes, entire byte has been read over this register. So, then we bring it down over here. So, this gets enabled and the entire thing is read over here. Okay. So, this register has been read, but as you can see, this data still has not been transferred to the output data which goes to the switch. Okay. So, that is being done with the other clock. So, this is where we take the switch clock. So, this is the switch clock we take. Okay. So, switch clock again we divide by 8, that means the boundary we actually fix. It is the switch boundary, that means exactly at what boundary we want to get this data read. Okay. So, at that boundary we actually enable this one, again this register. So, what happens? So, this data gets transferred over here. So, there is a slight delay when the data is getting read according to the clock input clock of the data, and the way data is being taken out to feed into the switch. So, there is a slight delay, this will be always happening. So, that delay is because of this desynchronization. Okay. So, once this is read, again this will be converted parallel to serial, and that is being fed to the switch. So, now with this operationally if we try to see what is exactly happening. So, let us try to see, suppose this is my time frame. Okay. So, in time what we are trying to do over here is, let us say this is the data input. So, these are the byte boundary actually, okay. These are demarked as byte boundary. So, at that byte boundary only data 8-bit data or each byte is being read to the register. So, this is the point where first data has been read into the register. This is the point where second data is actually fetched into or put into the register, and so on. This is what is happening. Now, while writing, that is with the switch speed or switch clock speed, right. So, there let us say, as I have told, there is a slight delay. So, with that delay now switch, this is the byte boundary of the switch. So, at this point switch will be trying to read something whatever is there in the register, remember. Okay. So, now switch this one, as you can see, it is slightly faster than the other one. Okay. So, you can easily see the amount of bytes is being transferred in this overall time, that is higher for the lower one, that means it is a faster one. So, it is reading little fast, whereas the writing is little slow, that means the incoming data is not able to keep up pace with the input. Okay. So, that scenario is happening. So, what will happen in that particular scenario? As you can see, at this instant what I can read, whatever data has come over here, let us demark it as A. So, data A has come, data B has come, data C, D and so on, E, F. Now, as you can see, he will read A over here. What he will read at this point? B has been already written, so B will be read over here, so on C. But at this point you can see there is a difference that is happening over here. So, over here as you can see, already C has been written in the shift register. So, now shift register is storing C. First time it has been read. So, this is reading C. Next, nothing has been written over here. So, C is still stored in shift register. So, therefore, if you try to now read, C will be again read over here. So, this is called the double read or double read. So, you are getting a double reading, and after that again D will be read over here, E will be read over here, F will be read over here. So, as you can see, the data sequences are good over this time. Only thing is that there might be occasional double read, and when this double read will be happening, if your switch input clock is little bit faster than the input clock. Okay. If the reverse happens, we can again demonstrate that. If suppose this is faster, the input clock is faster, but the writing clock that is little slower. Then as you can see, A, B, C, D, E, F, these are the data coming. I am reading A over here because I am having the last data available A. Over here I will be reading B, over here C, over here I skip this data. So, this is called the slip. I skip the data and I actually read E because E is already available. D was available, but in between no reading operation has happened. So, therefore, I read some data E. So, there is a slip, one data is missing, and then again next time I will be reading F, something like that. This pattern will be continuing. There might be, if my input is slower or switch has a slower rate, clock rate, then there will be slip. If switch has a higher clock rate, then there will be double read, and this will be at a repeated interval, this will be happening, and you can easily calculate with what repetition it will be happening. That depends on the difference or deviation in the clock frequency. Okay. So, if the clock frequency deviation is very slight, then this repetition intervals will be very high. So, at a very long, after a very long duration, probably this repetition will be happening or this slip will be happening. So, this depends on how much clock will be deviating. Generally clocks will be deviating by a very slight margin, but the problem is not that. Any clock deviation, we know that there will be this byte boundary mix up, but now what we are doing, because all of them are now being synchronized with elastic store. So, every data, their sequence might be little bit disturbed, but they are read at the exact boundary. So, the problem we were discussing over here, that if I have a switch and then inputs are being fed, so there was a disruption in the data reading because of desynchronization. So, this data was partially read in between, that will never be happening, because switch is now at the input by the help of this nice device elastic store is getting synchronized exactly. Okay. But now you might be asking, there is a very natural question that comes into our mind, that what will happen to the switching, because switching we have some discipline, and that basically all this switching depends on the address, and address is embedded in the time sequence, right, where the data is located within the frame. If these datas are, suppose let us say A is the first data, B is the second data, C is the third data, and this is the fourth data. So, in the switch you have seen we have a space switch, inside space switch we actually configure it that the first data should go over here. So, accordingly we have a logic. In the time switch also we have a logic that which data has to be swapped to whom. If these sequences are disturbed, then wrong data will go to wrong direction. Now, that is another problem because of elastic store, because the data sequences are getting jumbled up, because after C now E is coming. So, switch, if I do not do anything, it will treat E as if it is the data coming from this D, okay, and it will switch it to that direction. So, wrong direction data will be transferred. This is a big problem. So, we have to now rectify this, but this is a very easy thing to rectify. What you have to do, all the switch logic, that was soft logic. Okay. So, we had a software based logic implemented in hardware, right. So, what we can do, that logic can be easily changed. So, we can detect this event wherever there is a slip or there is a double read which is happening, that you can easily detect by putting a counter that how much is being read in between one write. So, if there is more than one read, then you know that it is a double read. So, you can immediately issue that because of this probably there will be disruption. So, your switch logic has to be now modified to some other logic. Once you do that, again the switch will be functioning properly. So, this is all that you will have to do to actually make it completely synchronized. So, now you can see, even if my data is asynchronous, even if my two inputs are having different clocks, I have no issues. We will install this elastic store at every input, they will synchronize it to the clock and byte boundary of the switch, then switch will do the switching. Because of this, because there is a mismatch of the input data, this one, there will be a loss of sequence occasionally because of the slip or double read we have already seen. So, that has to be triggered from the elastic store, and this message has to be fed back to the switch logic center, and switch logic will accordingly take corrective action so that the switching is done properly. Now, there is no desynchronization or disalignment, so that there will be partial read within a slot, that will not be happening, and if there is some wrong switching of data, that is also rectified because I already take this event double read and then I know what to do, what kind of switch logic manipulation we will have to do, so that the earlier switching is restored. Okay. So, as you can see, with a very simple device we can actually alleviate this particular problem, which is a practical problem, and we have to really deal with this problem. So, this is exactly what we could do. Now, you might be thinking that if this is a particular kind of synchronization loss, okay, that might be happening over the space. In some of the location there will be desynchronization, and we can easily handle this. But what will be now happening if we have a multiplexer desynchronization? So, that is exactly what we will be discussing next. So, let us try to see how do we manage the multiplexer. Okay. So, multiplexer again same thing might happen. So, you have these data which are coming. Okay. So, let us say these are the bytes. Okay. In the first this one A is coming over here, then B followed by C. So, these are the words encoded in the byte. Okay. Second stream also having some data P, Q, R, S, T, let us say. Okay. Now, if there is a desynchronization in the clock, if there is a desynchronization in the clock, then what will happen? This byte duration and this byte duration might not be exactly same. So, there might be slight deviation. Okay. Once you are trying to interleave them, so interleaving means within single 125 microseconds. So, I am putting data stream from both of them. So, we squeeze them, basically we increase the data rate, we have already talked about that, how we do multiplexing. So, we will be interleaving them one after another. So, A followed by P, and then again take B from here and then followed by Q. So, B, Q, C, R and so on. Okay. We do it this way. But as long as they are synchronized, no problem. But what will be happening if they are not synchronized? You will see that over a time this will have, let us say this has a higher rate, this will have higher number of bytes delivered, whereas this will be having lower number of bytes delivered. So, let me give one example, probably it will be very clear. So, let us say the first stream is having 6 such thing, okay, and the second stream within this is only having 5. Okay, because this is little slower. Okay. Now, I have to actually transfer them. So, what we can do at this instant, we can actually combine these two. Again at this instant, the slower one I am taking as reference, I can combine these two, okay, and I can keep on doing so like this up to probably the slower one. If I see, I will be over here, if I come, this will be combined with this one, but this will be left because this has 6 and this has 5. So, if I am combining in time, if you see over here at the output, if I combine with respect to the slower one, I will be able to 1, 2, 3, 4, 5, I will be able to combine 5 of them. But this last one will be left alone. What do I do with this? That is when people have decided that maybe we will do something else. What we will do? We will have this kind of encoder. So, basically let us say I make a frame over here, I am giving an example. So, I make a frame of 4 byte each. Okay. So, we take 4 byte from one of them and 4 byte from the other one, we take that. After that, inside the frame we are now adding redundant bit. So, we are giving one control bit C1, another control bit C2, followed by one control byte, let us say if we do it byte, or if we do it as bitwise, then it will be bit. So, it depends on bit interleaving or byte interleaving, whatever we have done. So, then another control, another storage. Okay. So, this is C and this is S. So, because 2 stream we are putting, so there must be 2 control and 2 storage, you will see why that is required. Now, what we will do? We have to see within this frame how many of this one has been supplied and how many of this one has been supplied. It might happen that one of them is having one extra. So, that extra has to be stuffed for the other one. So, what we are doing? In the control we are specifying the 5th one is optional, 4 over here in this example probably 5, 5. So, 5 we will be putting together one after another. Then the 6th one is optional. In 6th one what we do, through the control we say which one has data and which one does not have data. So, 1 and 0 is the encoding for specifying whether we have a data or we do not have a data. So, if we specify 0, then it means that we do not have any data for stream 1. If we specify 1, then we specify that next following byte there is data. Okay. So, followed by 2 storage byte, and this makes the whole frame actually, and this particular thing gets repeated. So, by this 2 redundant bit, what we are doing? We are actually stuffing. So, over here we have only 5 data, over here we have 6 data, we have to transfer the whole data. So, therefore, for the first one we specify over here 1 and for the second one we specify 0. That means, over here I will be putting the data from first stream, the excess data, and over here this is being stuffed, that means nothing is being put. So, this is where you are putting a extra space so that you can adjust their clock whenever it is required in a bigger frame. Okay. So, if there is a clock mismatch, immediately by adjusting this C1, C2 bit, you can always put somebody or you might not put somebody. You might be asking, okay, within let us say one frame which can take 5 and 5, this is desynchronized in such a manner that it is having only 5.5 bytes, then what do I do? Okay. Then the solution is again simple. So, in the first frame you do not stuff anything, you say for both of them it is 0 0. So, you just do not put anything. In the next frame definitely, because it is 5.5, in the next frame it will become 11. So, 1 will be extra, that extra you put in the next frame. So, like this with an integer multiple of these things you will be able to always manipulate the rate misalignment. Okay. So, this is very simple, you can always do that with whichever degree of misalignment you need, but remember it has a limit. The limit is within this one frame, if it has 5 and this has 7, it is so much misaligned that one is only getting 5 data, the other one is getting equivalent 7 data, then you cannot do anything, because you have only located one space for stuffing, not more than that. So, one data misalignment within a frame, that is possible, but more than that it is not possible. So, that you have to keep in mind. So, there is the restriction, it just says that how much, up to how much clock misalignment you can still handle, and all the data can be faithfully transferred. So, this is actually, this is called the stuffing. Okay. So, you can call it pulse stuffing, it is sometimes it is also called byte stuffing. So, or if you just do bit by bit, then it is bit stuffing. So, you define a frame, you put some redundant bit, and within that redundant bit you actually do this stuffing control, and then some extra space are kept where you put data. If it has extra data you stuff it, that means you just put garbage value, let us say some particular encoding which is not included inside it. So, basically you do not put anything over there, you might put just clock, so that the clock is not getting lost. So, you just put 1010 sequence probably over there, because this C control bit is already telling that that is a garbage thing. If it is 0, then you do not read that, right. So, you can always do that. So, that is the extra thing you put for pulse stuffing or byte stuffing. This is exactly what you do, and this has a limitation, as I have told, that up to some clock misalignment it can take, and always in practical scenario we know that the clocks are not heavily misaligned. If we say it is a 64 kbps data, it will be almost close to 64 kbps, it might be 63.9 kbps or 63.99 kbps or 64.11 kbps, something like that, but it will not be misaligned by a heavy margin. So, these things will always work. Remember, there are certain issues over here. The issues are, this control bit are now very important bits, because if you do not know what is there in the control, or if you do not know, if the control bits are somehow due to error gets flipped, then you will be completely misreading the data stream. Whoever does not have any data which has been stuffed, you, if 0 becomes 1 in the control bit, you will be unnecessarily reading that data. Okay. Whoever does have some data, you might miss them if the 1 becomes 0. So, therefore, these two control bits are very important. So, generally you have to make them error prone, you have to protect them from errors, because it is a digital transmission. So, there might be this bit flipping that might happen, there might be errors. Okay. So, due to different reason, there might be noise, there might be interferences, so all kinds of things might happen. So, due to that there might be erroneous data reading. One data getting erroneous, okay, that is not that severe, but this control bit getting erroneous, then you have a whole byte because of this probably will be misread. So, because of that, generally you give protection against the failure or error proneness of those data. So, what you do? The first thing is you generally keep redundancy over there. So, what do I mean by redundancy? That means this C1 bit, you actually put multiple C1 bits, okay, some even number of maybe 5 or 7 or 3, something like that, and you will be putting same thing over there. So, suppose I want to put some data in the first stream. Okay. So, in D1 I want to put something. So, this must be 1. So, I will be putting 1 in every C1. What does that signifies? That even if there is a, and then what I will be doing? I will be taking this and then vote among these bits. So, if there is an error, one of them might be erroneous, but these two will still survive, and because of the voting I will get 2 out of 3 are 1. So, therefore, I will take 1. So, even though one bit is erroneous, I will still be able to decode it properly. So, this is often being done, but remember, often this errors comes in burst. That means, one bit is erroneous, the neighboring bits will be erroneous. So, that is why within the frame you generally distribute these C1 bits. So, that means you can put C1 somewhere here, C1 somewhere here, C1 somewhere within the frame, you distribute them, so that a burst error never actually sacrifices your error protection. Okay. So, this is often being done. So, basically what you will be doing, you will be reading all these things, then all C1 you take a voting among them, whatever is majority you then say, okay, this is my decision. So, I should get a stuff byte, and accordingly will be deciding whether it is a proper data or it is not a proper data. Okay. So, that is the whole discussion about synchronization that we have so far done. So, basically we have discussed about two kinds of synchronization. One is for the multiplexer, because we had two devices over here, we have introduced two devices. One is multiplexer. So, multiplexer synchronization we have already seen how to do deal with that. Similarly, demultiplexer will be just doing the reverse thing. Okay. It will be decoding them. So, basically from that reading, the way we have done this pulse stuffing, it will do just the reverse thing. So, you will be able to get the data properly. And you have switches at the switch input port. If they are desynchronized, then switch will be doing partial switching, which will completely disrupt the data. So, for that we have started installing elastic store. Elastic store at least make the data exactly aligned to the byte boundary of every slot of the switch. That is good, but due to that elastic store we have seen also that there might be either double read or slip. So, you take that input from the elastic store and accordingly rectify the switching characteristics, or I should not say characteristics or switching logic, so that it does still the correct switching, because he now knows what is the shift in the location. So, accordingly he will just reinstall the switching logic. Okay. So, with this probably we have finished our synchronization issue. So, that means what we have so far done is we have seen what are the components required in a circuit switch network. Okay. Circuit switch network is something where you first establish the connection, okay, and after establishing the connection you actually send your data. Okay. So, over here we have also appreciated that it is TDM multiplex. So, the multiplexing is TDM, that means exact location is his address. So, with respect to the location, switch decides where to switch it. So, basically the switching and everything happens through this. Then we have seen what are the components that are required for circuit switch, for facilitating circuit switch network. So, one is of course the multiplexer or demultiplexer. Then that actually generates from lower data stream, do the time division multiplexing and generate higher data stream. Once we have multiplexing, after that it is switching. Then switching also we have evaluated what kind of switching there might be. So, we have seen that there is a space switch, there is also a time switch, and there is combination of these things. We have also discussed about the advantage, relative advantage and disadvantage of this space switch, time switch, we have done that. Okay. After seeing that, we have after that we have started discussing about the performance of switch or switch design characteristics or criteria. So, there we have discussed about one very particular quality of a switch, that is called the blocking probability. We have also tried to evaluate what should be the efficient design of switch, that is something we have tried to evaluate. How we reduce the switch complexity, that is something we have discussed. We have also discussed the control of the or control logic of a switch, how much memory is required for control logic, that is also we have evaluated. And then we have also discussed that what should be the characteristics of a switch. Should it be a completely strictly non-blocking or rearrangeably non-blocking or a blocking switch? If it is blocking, then what will be the associated blocking probability? How do you evaluate those blocking probability? What are the guiding equation, Lee's graph we have discussed, and then we have started actually evaluating that for a particular targeted blocking probability, how do we design a switch? And we have seen the multi-stage switches also by combining time switch, space switch, multiple space switch. So, all those things we have seen. At the end, we have discussed very important aspect of circuit switch network, that is the synchronization. We know that there will be loss of synchronization because it is a spatially dislocated network. So, different components are at different location, they are getting input from different locations. So, they will be desynchronized. So, that desynchronization, how do we handle them from engineering design perspective, that is also something we have appreciated. So, that completes the whole gamut of circuit switch network probably. So, over here we will end this circuit switch network, only one topic which is left. We have seen how to evaluate the space switch, and those space switch were not, we have also discussed space switch or any switch. There are two kinds of switch. One is the local subscriber loop, they are the switch where it is some input port to some specific output port, but we have also discussed there is a switch called trunk switch. In trunk switch, the output ports are not specified. You have multiple output port, they are like server, any of those port you can take. So, it is a kind of any switching, whichever is available. So, this trunk switch we still have not characterized it, that means we have not analyzed it. How many trunk link we should put, so that we get some amount of blocking probability. So, this blocking criteria cannot be resolved for trunk switches through Lee's graph. That is something we will be now exploring, and that is where a very fundamental theorem comes into picture, which is called queuing theorem. So, what we will do, we will go a very brief, this is not the course of queuing theory of course, but we will do a very brief overview of this queuing theory, and then we will see how to evaluate a switch, especially a trunk switch. That is something we will be discussing next. Thank you.